Good afternoon, ladies and gentlemen, and thank you very much for joining us once again for this in the PDH series. My name is Alan Geary, and my colleague Thomas Wynant may not be joining us. He's been called away to some site measurements that we're doing, and no doubt that will hit the headlines in a few days' time. So what we're talking about today is the design, maintenance, and bridge failures with efficient mitigation measures. Now, the point about this is, to start with, why do we build bridges? And the basic point here is that we are building them to span waterways or go across chasms to get people from one side to another. And we're assuming very often that there is a process in which we have a well-known environment to work in and that it is benign for us. Well, that isn't always the case. And I'll take you through some of the things that can happen. Additionally, we assume, or we have assumed, in the days of building bridges, that we know pretty much all of the environmental forces which are going to impinge on the bridges. We've been very wrong. And in fact, the latest developments have only happened, well, the very latest have only happened within the last few years. But one of the biggest ones is the identification of wind forces on bridges. And that has taken off really in about the last 70 years. But a lot of our bridges are older than that, and there are implications. So I'm just wrestling with my computer to make sure that we can advance to the next slide at the moment. Bear with me. While I'm waiting for this just to catch up with me, I should perhaps mention that both Tom and I work very largely in the field, gathering information, and that's what I'll be talking to you about today. I have two doctorates, or a PhD and a higher doctorate, and I'm both a structural engineer and an electronics engineer, and I am a fellow of the Royal Society. Tom is a professional engineer in the state of New Jersey, and together we form a team which has a lot to tell you about. Okay, I am starting the PowerPoint again because I think that'll probably be the quickest way to get it to you. Here we go. And apologies for the delay. So this is what the presentation is going to cover today. It's about types of bridges, the reasons for failures, and how we can quantify the performance of bridges from measurement to identify weaknesses. And then we look at bridge design considerations through the ages and shortcomings that multiply themselves in the environment. Instabilities caused by wind, traffic, and aging. So, sorry, are we having a problem? Let me share my screen again then, and so can everybody see the screen okay now?
Yes.
That's good. Please accept my apologies. The machines are trying to fight back. So here we go. This is what we are covering today. There are the types of bridges, reasons for failures, quantifying the performance, looking at bridge design considerations through the ages. And this is it. I'll be talking about the history of some of the more important events. Instabilities caused by wind, traffic, and aging. The history of bridge damage and failures. Damage detection using advanced methods. Bridge maintenance, including loose connections and suspension bridge checking. Accurate measure of the natural frequencies and damping of bridges and the risk ratio to quantify damage for biannual inspections. And then practical information about bridge response. So first, let's just look at the 7 major types of bridges. We have truss, cantilever, cable stayed, suspension bridges, arch bridges, beam bridges, and tied arch bridges. Now, quite often, there are bridges which are a mixture of some of these types. Sometimes that's a good thing, sometimes it's a tragic thing. Okay, so if we look at the identification of the way that bridges actually behave, I'm going to jump straight in here and say this is about the dynamics of structures. But I'll explain to you as we go through exactly why that's important and how we can actually draw a parallel between dynamic and static behavior, and particularly how it impinges on design. So the first thing is system identification. System identification is a question of treating the bridge as a system and then applying mathematics to define how that bridge is, how it behaves in the event of forces impinging on it. So the first thing is each mode of vibration has a frequency of resonance. This first one here shows the normal sort of thing that we consider for bridge design. In this case, the center of the bridge is going up and down. But modes of vibration as frequencies get higher are higher, and the modes of vibration are more complex. So in this particular case, we get something like a wing flap of the bridge. And here we get an antisymmetrical mode. Here we get another antisymmetrical mode in which one half of the bridge is going up while the other is going down. And then the modes get more and more complex indeed. Each one of these will represent the stiffness imparted by a little part of the bridge. So we use this sort of thing to identify what we need to put into a finite element model if we want to use the finite element model for identifying what will happen under bigger forces. Through measurement of what happens in the bridge itself, we can calibrate the model. If we haven't built the bridge as yet, then we have to make a number of guesses, and that can sometimes be a problem. I am running into another problem with the computer at the moment. Hold on, I will just restart this again. I'll be back with you in just a little moment. So can you see my screen at the moment? Okay, here we go. I think this should be okay now. You should be able to see Sydney Harbour Bridge at the moment.
Yes.
Good. Now this is one of the major types, but it's an arch bridge. And if you look carefully, you will see that the arch is not connected to the towers that would normally support an arch bridge. Oh, I have the same problem again. Hold on just a moment. Sorry about this. The next slide is the Yokohama Bridge in Tokyo, in Japan, in which we see cable stayed action. The next one is the Qingma Bridge in Hong Kong, and this was before it went into operation. It actually is cable-stayed bridge and connects the new airport to the center of Hong Kong. And of course, with cable-stayed bridges, what we actually have is a particular problem which came to light with the Tacoma Narrows Bridge. And I'm sure those of you who know about bridges and know about wind engineering will know that this was a dynamic response of the bridge. This is the Tacoma Narrows Bridge these days, in which there are new bridges, both of them cable stayed, and they allow traffic to go in both directions. We have here an example of what happened in San Francisco. The problem here was caused by the Loma Prieta earthquake, which was a magnitude 7.1 in October 1989. The upper level of the Nimitz Highway was collapsed, and a number of people died. And cars were crushed between the two levels of the Nimitz Highway. Now, quite by chance, I was giving a lecture to the Hong Kong Institution of Engineers on 17th of October, and I was talking about the random processes that involved with earthquakes and with wind engineering. I happened to be talking about San Francisco as an example as well, and was phoned very early the following morning by the head of the Hong Kong Institution of Engineers, who said, "You're absolutely clairvoyant. You told us it was going to happen." Well, I may have told them it was going to happen, but not that it was going to happen today. Anyway, that was a coincidence. So the question here is, what causes bridge failures? And there are two main categories: management and environmental causes. With management, that can be cut down into design errors, construction errors, inefficient maintenance, and material quality deficiencies. For the environment, we have environmental actions such as earthquake, wind, flood, fire, etc. And of course, these earthquake, wind, and flood and fire are random processes. What we do these days is to identify how often they are likely to happen, or at least on average, how often. We're assuming that our environment will stay the same, which it doesn't. We then have extreme loads. Extreme loads can be caused by collision or overload. And in fact, we've been involved with some overload instances. And of course, the one which authorities like to blame most often is human error. So if we look at that in detail, well, the first thing is use statistics with caution, because in the statistics, very few earthquakes are actually included. And that's for two reasons. The first is that it's difficult to include them in the statistics anyway, because earthquakes are of different amplitudes. They have different types of energy in them as well. And secondly, they are a random process which has a much longer time between occurrences. So what we have is in the management, normally there are multiple reasons for errors occurring. And these can be construction errors, amongst others. The US actually shows in the statistics that construction errors are less than in other countries. But of course, this may be that fewer bridges are built in the US right at the moment. So we have 70% of bridge failures are caused by environmental issues, and the large majority of those are actually wind induced. So now, what do we need to know then? First, there are doubts about the continuing integrity of bridges. Secondly, there can be visual evidence of aging. Thirdly, there are new design considerations, and some of those are really pushing the envelope. Fourthly, there may be a change in perceived risk, like taking bigger loads across bridges, like the environment changing. And so this presentation is all about a number of different things, including an alternative approach to assessing structures, bridges especially, and assessing the need for ongoing maintenance with an implication to the life expectancy of bridges. So what we're doing here is looking at taking a measure of an event occurring. This might be an earthquake or it may be a windstorm. And we can make a measurement before the event and after the event. And we calculate what the difference is, whether things have changed before and after. At the moment, the main method is to monitor during the event, to wait for the event to happen and to see what the changes are during that. There are big problems with doing that because the structure itself, especially if it's taken near to its limit state, may well be having nonlinear behavior. So the problem here is that if you try over a short time to look at this nonlinear behavior and see what is happening in it, there just isn't enough time to be able to do that accurately. However, if you take the before the event and after the event, you've got a lot of time that you can spend looking at the response of the structure. And you say, okay, but it's a much lower amplitude. Yes, that's true, it is. But I'll come back to exactly why that's not a problem for us. So if we do make these measurements at low amplitude, then what we have is a new approach requiring new technology, and we have advanced algorithms. We have extremely accurate analysis of dynamics, and we can compare what has happened to a structure during a large event. And it can be used for tracking damage. But this isn't in opposition to the traditional way of checking. It actually complements and shows you where to look for particular problems. So let's take a look. There's an infrastructure report card produced for the United States in 2017. US has 614,000 bridges, of which about 40% of them are more than 50 years old. Now that's important. The other thing is that 9% of bridges at the time of the infrastructure report card were actually rated as structurally deficient. Now, structurally deficient was actually defined as being not up to date with the codes of practice as they were now. Well, of course, if they were built 50 years ago, a lot has happened in that time. So this structurally deficient actually said they aren't built according to our current day codes of practice. They were okay when they were built, but they're structurally deficient because they do not have the same sort of safeguards that they would have if built now. The estimate for how much it would take to bring all of these bridges up to the modern code of practice point of view, would be $123 billion, at least in 2017 dollars. So here we have America's bridges by age, and you can see that just about 40% of them are 50 years or more old. Now, 50 years is a very significant time because that takes us back to 1980 and 1970, and around 1970, changes in the wind loading codes of practice were legion. And you can see a smaller and smaller percentage as we come up to modern bridges. And this is the number of structurally deficient bridges, both by number and by age. So you can see something has been being done about it. The number has reduced, but it's still a significant number which have not been brought up to date. I want to go back to the Tay Bridge disaster in 1879. The reason being that this was absolutely a watershed for bridge design. 1879 was a very important year. Before that time, we were using deterministic loads. We used 10 pounds per square foot as the loading on a bridge. So when trains sped over the bridge, they created loads which were covered by that. There was, in 1879, a disaster. There was a storm, and it blew and destroyed part of the bridge. The train was on it and fell, killing over 200 people. The design itself was compromised by cost requirements. The train which was destroyed was actually going north. The wind gusts, though, were only probably 65 miles per hour. So 10 pounds per square foot was not a very good indication of that. And the winds in Scotland were potentially anyway, much larger than wind gusts of 65 miles per hour. However, there are nuances to this because the designer was the Astronomer Royal in the United Kingdom. And as soon as the disaster happened, of course, he was the scapegoat. He lived out his final years in poverty and was an absolute villain as a result. However, 100 years after the collapse, it was found that it wasn't a question of what the loading was, it was a question of a fatigue problem. So the fatigue problem was the problem, and this fatigue behavior occurred in lugs which are shown to have started at 50 mile per hour gusts. So in practice, 10 pounds per square foot was a silly way to design the loads anyway. So what we've got is the Tay Bridge disaster. We've got a progression up to the current day. So we had the Tacoma Narrows Bridge failure. We had, up until 1950, codes were prescriptive. And that actually means that what we had was an identification of exactly how you should build a bridge, not a question of identifying what the loads were going to be and designing for that, but telling designers that you had to do it this way. In 1989, we moved to a different type of prescription with codes of practice, and this allowed us to set goals to what the behavior of a structure should be. And it's only later, much later, that we had performance-based codes and codes in which the randomness of winds and earthquakes were actually taken into account. However, at the time, what we did was we went from Tay Bridge, where it was £15 per square foot. If the Tacoma Narrows, we took £30 per square foot directly as a result. Then the question of dynamic effects came into account. And you can see clearly in the Tacoma Narrows, dynamic effects were what we needed. So even up until about the year 2000, the codes were prescriptive. We had NIST, National Science Foundation, identified performance assessment goals, and we moved towards those. So only in about the last 23, 24 years do we have risk and performance regression. And that's important. I'll tell you about how that actually occurs. The Brooklyn Bridge in Manhattan. Construction started in 1870 and it was opened in 1883, 4 years after the Tay Bridge collapse. It was a suspension bridge and it was hybrid. If you look carefully, you can see that the suspension cables are actually not vertical. They're a combination of vertical and horizontal. The bridge itself has been renovated in the 1950s, 1980s, and 2010s. There's a very interesting occurrence that occurred, though. On the Manhattan side and on the Brooklyn side, the towers were built on caissons, and the caissons were filled with air under pressure, so that removal of earth could occur until they got down to bedrock. In practice, on the Brooklyn side, that was relatively straightforward. They didn't get to bedrock, but decided that it was possible to work with what they had. On the Manhattan side, they went further down and did not get to bedrock. Those of you who know the geology of the Manhattan area, you know that there are individual rocks in various different places, surrounded by clay type soils. So they may or they may not have hit it. That meant that they had to pump air into the caissons. They had a number of cabins inside there, which they didn't know about the bends in those days, which is working under pressure and then coming back to atmospheric pressure. What happened then was that people got the most awful headaches, and the action of little bubbles appearing in the bloodstream, which caused problems in the human body. They didn't know that it was the bends or anything like that, though, and they called it the caisson disease. Well, John Roebling was the designer originally, and his son, Washington Roebling, continued after John Roebling became bedridden. And he, though, had a problem working in the caissons. He himself suffered such terrible problems that he was bedridden. And his wife, Emily, used to take written commands from him to the construction team, and she eventually became the project manager of the whole thing. So she took it to finalization. She was good at maths, good at knowing what catenary was, various things like that. So it was lucky that Washington Roebling had a very able wife at the time. So we moved. The history of bridge development from that time has taken going from a code requirement of 15 pounds per square foot to a quasi-static loading, which then changed to include dynamics as well. We can take the frequency of a bridge, excuse me, and we can look at what that means. The thing is that with long span bridges, the natural frequency of a bridge tends to be very low. And I'll come back to that a little bit later as well. What this means is that you have the possibility of instabilities, aerodynamic instabilities, caused by the bridge having very low frequencies of resonance and the wind having a lot of energy in it at very low frequencies. If we'd understood that when the Tacoma Narrows was built, we might have avoided that problem. Well, it went further. There was work done by Ellis and Cantini, which showed that there was a frequency correlation with the structural dimensions. So as the bridge deck gets longer, then the natural frequency goes down. It's much more of a problem than it is with tall buildings. You get down to extremely low frequencies with bridges much more easily than you do with tall buildings. At least at the moment we do. We then had nonlinear damping characteristic, which I'll talk more about a little bit later. Ron Mays experimented with motion beyond the elastic limit and looked at how that might be important for buildings and bridges. Kit Scruton at the National Physical Laboratory in the UK worked on aerodynamic instability, and particularly the sort of instability that had caused the Tacoma Narrows disaster. Kit Scruton had defined exactly what the mechanism was and the equation which would define the speed of the wind which would create an instability. And so we have the Scruton number, which defines exactly how we calculate that. The interesting thing about that is that we've looked at these instabilities and found that you can go even further. You can look at the instability at various different speeds of the wind. In practice, what we can do is to say Tacoma Narrows, if the wind had been stronger, it would not have excited the bridge in the way that it did. And so the Scruton number depends on the shape of the bridge. VC is 5ND. 5 is actually the Scruton number in this particular case. N is the natural frequency, and D is the main dimension of the bridge itself. So you can tell quite easily exactly what the speed of the wind is going to be to cause this flutter type of instability. Well, you saw there were lots of modes of vibration of bridges, and so there are lots of different speeds which will cause an instability in different modes of vibration. And then we moved on to looking at the way that the wind actually behaves. Alan Davenport and Scanlon in the United States did a lot of work on this and revolutionized the way we looked at the way that wind behaves. Under these circumstances, we can actually identify how probable it is that a particular wind speed will occur. Absolutely ideal for the design of bridges. And here we have some of the errors. Firstly, we have design errors, which uh, which cause construction problems and ongoing problems during use of the bridge. Here we have scour occurring. It's particularly big problem in this particular bridge. And we looked at in the Mosholu Bridge in New York City, we looked at the question of scour for this particular bridge and found a peculiarity. We simulated this particular bridge with scour 1 foot, 3 foot, 4 feet of scour occurring. And we looked at the frequencies which occurred. So we had calibrated our structure, looked at the modes of vibration, and then identified them. Now, if we look at the ratio, the modal ratio, then what we find is that that changes a small bit if you're comparing the frequency of the second mode to the first mode. Same with third to the second, fourth to the third. But if you look at the fourth to the first, then this diagram here will show you what that ratio is. And in practice, it says that just simply by comparing the first mode with the fourth mode, you can actually identify if scour has occurred without sending divers down to have a look and see if it's there. Just simply by measuring the natural frequency of the bridge and looking at not just the first mode, which is used for design, but also the fourth mode. And then we have impacts. Two basic types here. First, river traffic going into the supports for the bridge, and road traffic. And then we have the possibility of instabilities caused by overloading. And in this particular case, you can see that the side of the bridge here has had a torsional vibration or torsional buckling type of loading, which caused the collapse. And we have excuse me just a moment while I again fight my computer. Okay, so moving on now to the Florida International University bridge collapse just recently. This is a very interesting occurrence because this is a monotruss bridge, but it's styled, or it was styled, it would have been styled to look like a cable stayed bridge. This was the original design. What you can see here is that we have a truss section here. We have the walkway and we have a roof, and then the truss is created along there. The concrete truss depended on post-tensioning cables, and the post-tensioning cables went through to the walkway. And what it meant was, and this is the NTSB found that the cause of the collapse was a miscalculation of resistance of sliding of the connection between the walkway surface and the truss that held it up. So once that has gone, then we've lost the stability of the entire structure, and that's the failure that occurred. Here we have Marcy Pedestrian Bridge in New York State. There was a similar failure in Sweden as well. What we had in this particular case was, in practice, a steel tub girder, they were calling it at the time. In fact, it's subsequently become known as box girder. And what was happening here was that there was a buckling mode which occurred in the box girder. The recommendation after the event was that there should be diagonal bracing between the top flanges and lower down. So having done that, we got rid of the potential problems. In this particular case, the Skagit Bridge, which was built in 1955. Again, we're looking at the time of a change in the way that we were identifying what wind loads would be. Not that that was the case in this particular case. What we had was a bridge built in 1955 and was considered functionally deficient. In other words, it didn't meet the standards of the codes of practice in 2014. So, which is when the collapse occurred. This is over in Washington State. In practice, what had happened was that a truck had driven on the bridge and had collided with a number of these truss members in the bridge, and we had a failure of a single section. Why was it functionally deficient? Because it didn't meet the current day code of practice, but the current codes of practice actually say there must be redundant structural members to maintain structural integrity. Now, this is incredibly important considering what has gone on in Florida just recently, and that is that every structure must be assessed for structural integrity by the end of 2024. So this is coming. You must be aware of the fact that you have to check for structural integrity. If a bridge is more than 50 years old, it's impossible that the designers originally assessed it. They could well have done everything they were required to do and still have something which is functionally deficient. And then we had the Ponte Morandi in Genoa, Italy. It collapsed, just got old, and section of the bridge collapsed on buildings below. But it only took 22 months to rebuild this section which had fallen, and it cost $216 million to do it. Now, the interesting thing here is that the Ponte Morandi was actually a method of going past a town which the people who lived there were very keen on. They didn't want the traffic jams of people who weren't interested in stopping in their town. This is a bridge in Sao Paulo, in Brazil, near the Rio Pinheiros. In this particular case, once again, it got old, and it got old because of errors with the supports to the structure. And if you can see here, you can see that the viaduct fell by about 2 meters here. So once again, you lose a complete freeway if this sort of thing happens. And then there is the King Street Bridge in Melbourne, Australia. The collapse occurred in 1962. Once again, very close to that change in wind engineering, although that was not the major problem in this particular case. This is a welded steel girder, concrete deck, cantilever suspended span, and it one span collapsed under the weight of a 47-ton semi-trailer. In practice, though, the weight of the trailer was within the bridge limits at the time it was built. There was an Australian company and a US company which were both working on what was going on. J&W chose high tensile steel for the fabrication. Both companies were unfamiliar with welding of high tensile steel. In practice, they had used a British standard, and then knowing that there was a problem, that the standard didn't cover high tensile steel, there was a little addendum which both companies ignored. So they both misunderstood the requirements for high tensile steel. The specifications were not very well met anyway. They were not very well written anyway. So the commissioners said that the cause of the collapse was we hardly know who to blame the more, J&W for its cavalier attitude or CRB for putting up with it. So you can see the original decision was J&W. CRB just accepted it. You cannot run away from your responsibilities. So what do we do about these things? The first thing is that visual observation is very variable. You can look at the way a bridge is behaving, and you can miss things. Checklists that are given to surveyors quite often are based on opinions of what's important and what's not. If you make measurements, they can be precise, and an analysis can be about holistic behavior. If you're looking at the dynamics of the bridge, you don't necessarily have to measure in lots of different places. What you do is you measure holistic behavior so that you measure anywhere and you see the behavior of the entire bridge. Nevertheless, the analysis and the implications must be thorough and subject to peer review. Well, there's something going on at the moment, and that is that people are saying, okay, we can drive a vehicle over a bridge and we can monitor what the bridge is doing as a result. Forgetting, of course, that the vehicle itself is a dynamic system. So what they've done is to say, okay, we can measure the system properties of the vehicle, and we can use that then to measure the properties of the bridge. There is a problem with the roughness of the road because that will put a force into the structure. which may not be um, absolute, but nevertheless, it has interest. It's being used or experimented on by a number of universities at the moment. So it has possibilities. At the moment, there's still some way to go. In 1989, NIST produced a report. 48 recommendations were made. So it was basically saying sensors and measurement techniques for assessing structural importance are incredibly important. So 30 years later, most have materialized, but some did not. The key recommendations that are not broadly applied as yet is that a finite element model needs to be calibrated against measurement. Second is that damage detection and identification of the bridge behaving as a system is a nonlinear system and it requires nonlinear analysis. But nevertheless, measurements for the assessment of performance are important and incredibly powerful. This one has not yet been recognized. And it said we should share information between countries. Well, at the time of this, I was working in the UK, and NIST and the Building Research Establishment did work together quite a lot. So, bridge assessment, what do we do? We use Newton's laws of motion. They are an approximation, but they're good for operating within a linear elastic range. Satisfactory, therefore, for engineering purposes. And all we need to know is the mass which is involved, the element and overall geometry, their stiffnesses, the input forces, the response, and damping. Damping is the most difficult one to assess. In fact, what damping is the dissipation of energy. The point about this sort of thing is that instead of working up from the individual element properties, we can work down from the holistic response. So if we assemble a whole series of elements, we can identify those quite well. But then when we attach them together, we do not know how they interact, what the transmission of forces is. Whereas if you work from the holistic response, what you can do is work down into the detail of the individual elements. In fact, in my opinion, it's a superior philosophical way of going about it. So the problem there is avoiding the problem of description of the connections. Anybody who's done finite element programming will know that you're asked to put in how the interaction behaves. If we take Newton's second law of motion, we have force equals mass times acceleration. And if we look at this in more detail, we find that we've also got other forces: damping, energy loss, and stiffness. So if we use these, then what we have is we look at the response, we take the force, and we have stiffness, and then we have a dynamic component here. In other words, if we set the frequency to 0, we have the static case. We get the response is the force divided by the stiffness, which we're all familiar with. We all did it in university with our laboratory experiments. However, nothing behaves purely statically. In fact, for a structure to fall down, it is most certainly not static. If we, instead of setting the frequency equal to 0, we set the frequency to resonance. Then what we find is that response is force upon stiffness, exactly as before, and then we have the dynamic amplification factor. So you see, we've simply said that the frequency is R here and it's 0 here. Now, stiffness and dynamics. Here we go. This diagram actually tells us what the response of a system is against frequency. So the frequency, F upon Fn, is 1 here. That's the resonance frequency. And then the frequency gets larger and larger. So at very low frequencies, 0 frequency here, you get a 1-to-1 value. At resonance itself, you get this dynamic magnification factor, and this is the equation which governs the whole of this that's shown here. And what we have is a dynamic magnification factor of 1 upon 2 zeta. Zeta is the damping ratio. So the less damping that there is, the larger the dynamic magnification factor is. But it's not that simple. So what we can say, though, is that statics is a special case of dynamics. It's simply a dynamic system in which we've told it that the frequency is 0. So resonance is excited by natural actions like winds or earthquakes. The bigger or lighter a structure is, the more likely it is to be excited dynamically, and that's because the damping is likely to be less as well. The dynamic response is very important for bridges. Why? Because the frequencies are lower and the wind blows every day at the low speeds, which are important for creating aerodynamic instabilities. So damping actually divides wind and earthquake engineers. Why? Because wind engineers have been used to measuring the response of structures over long periods and say, yes, we can identify what damping is. Earthquake engineers say, we don't have enough data. We only have a few minutes at the maximum when an earthquake is going through. So what we do is say, yeah, okay, we'll take an average value. They also have the problem that it's not just the structure, it's the soil structure interaction, which is important. So in other words, we've got two problems in earthquake engineering. You can see what the changes in frequency must have been, but it's very, very difficult to identify what they actually were from measurement. Damping changes 10 times more than the frequency changes as the amplitude increases. So in other words, it is much more important for this. And that's why in the earthquake engineering world, people have decided the thing to do then is to look at the response of structures, just the frequency and the amplitude. Let's forget damping because it's too difficult. In wind engineering, they've said, no, we know that a lot of things are caused by low damping ratios, and we get failures because of that. So it's difficult still in wind engineering, but it's not impossible for long-term random excitation. At large amplitudes, other nonlinearities apply: soil structure interaction, radiation damage, modal coupling. But damping actually, although it's difficult, it carries a lot of information about the structure and how it's behaving. Solution is measure at low amplitude for a long period of information before and after an event, and you can see if things have changed. When we enter the nonlinear zone, stresses redistribute. There is now a move to understanding failure modes. Every nonlinear, even nonlinear programs rely on linear approximations. We're moving beyond that. We're beginning to, as AI becomes more important. However, we're not there as yet. So for the time being, we should be looking at overall behavior, and this has a direct relationship with modes of vibration, with modes of failure. This is the Van der Hoeven spectrum, and this is why wind engineering is so important for bridges. Here we have the micrometeorological peak, and this is one cycle every, and then we've got 10 seconds, 40 seconds, we've got one cycle per hour, we've got semi-diurnal, we've got one cycle every 4 days, and so on. So what we actually have is this area here, micrometeorological. As our bridge decks get longer, we work our way up this characteristic, meaning that as they're longer, we get bigger and bigger forces until we get to about one cycle every 40 seconds. And that's the maximum of the micrometeorological peak. So this means that we've got a little bit of a problem. Doesn't matter how long we build, then this actually tells us that there are eddies which occur, bigger eddies for these very long period responses. And what that means is that we can get this vortex excitation. Again, we go back to Tacoma Narrows because this was occurring and caused the collapse. What we have here is, in fact, I've shown this with a circular section, but it works for bridge sections as well. In practice, the vortices occur first from one side, then the other, and you get a vortex street occurring. The natural force on the structure is then varying and will excite the structure. As I said before, Kit Scooten produced a formula for that. For this particular case, the wind speed is 5 nd. And there it is in practice of a bridge, which I'll show you a little bit more detail. And we've found there that the natural the response of the damping response changed considerably at low amplitude once we got up to a speed which was sufficient to excite those vortices. When the wind was lower, we didn't get any of these vortices at all. When we went to one of the biggest houses in North America and we showed them what we got, they actually said we just couldn't do that. And why not? Because these vortex sheets were created at 0.2 hertz. So you can see we had a resonance that we were analyzing here of one cycle every 5 seconds. So it's interesting. If you stand on that particular bridge and you cannot feel the vibration, and yet if you look into the distance, you'll see what appears to be the Earth moving up and down. So if you're in the linear elastic range, displacement per unit force is a constant. We use Young's modulus. And we wouldn't if we didn't think that displacement per unit force, stress strain, if you like to use it in the very small, then that's Young's modulus. It is for entire structures as well, where we're looking at displacement per unit force. So if you're looking at the behavior of entire structure and you're now looking at the very small vibrations, what you have is you exclude soil structure interaction because that only occurs at higher frequencies, and you have Young's modulus or its equivalent working for you. You get the displacement per unit force characteristic, which is a constant all the way up to the end of the elastic range. So the response is governed by the structure. We only need information about frequency, damping, and modal displacement to be able to determine displacement per unit force. And the design forces are stipulating codes anyway. Complication, though, is that frequency and damping are nonlinear. So how do we get over that? Well, just briefly, I drove this big vibrator system on 40 different full-scale structures. This is an example in which the force was varied, the frequency varied, and the damping varied. And if you look at the decay of oscillation, then what you get is the instantaneous damping value, rising to 2.65% and down to 1.37%, while the frequency changed from only 1.32 to 1.30. And if you look at these decays of oscillation with a practiced eye, you can see that there is a change as the amplitude goes down. And I include this in because it may not be a very good diagram, but it was taken contemporaneously. So this was taken at the time we were doing the tests. So indication of damage. As long as everything obeys Newton's laws of motion, we're okay. 18th century physics then is sufficient for our purposes. But we still have this problem with the interface of part of the structure and the support. And we spend very little time researching or even learning about this in universities. So a performance base. If we solve the equations of motion at resonance, then we find that the value for a single resonance is dependent on 1 upon 8 zeta f squared m pi squared. That means that to measure displacement per unit force, we only need to measure displacement, the damping, and frequency, because we're going to compare what we're actually measuring with what the codes of practice say we ought to have. That means that mass is the same in two cases. That means all we have to measure is damping and frequency. So we can do that, and it's easier to do it with wind because you can take the measurements for a long time. You can't do that with earthquakes. So the baseline approach says physics, math, system theory, fracture mechanics, structural engineering are all behind it, and really good instrumentation. So measure the performance, analyze, and compare. What we then have is a baseline for a structure. When it's new, we should get our baseline. If we can't do that, as early as possible, and then we compare with what the code of practice actually says. Now, does it say anything about frequency and damping? Well, yes, it does actually. So the thing about this is that all structures are moving all the time. Very small vibrations, but most codes assume that we've got elastic response. So we take that, we measure frequency and damping, and we have good instrumentation because we want to know about these other modes of vibration. Here we've got frequency and we've got the amplitude measuring on a structure. So if we have a noise floor, which is only at this higher level, then we miss all these other modes of vibration. So in other words, could I measure using my iPhone? No, you can't. You need a really good instrument which takes the noise floor right the way down here and shows you what these other modes of vibration are, because they are the key to identifying where the problem occurs. Is it in codes of practice? Yes, it is. In practice for buildings, it's rather more easy, but in practice, we have Cantini's work showed us this graph here. The frequency using a lot of European bridges was gives us an equation which is pretty good actually. It shows that the frequency is proportional to the length of the main span of the structure. And then damping. Damping is correlated with frequency as well. Now there are fewer dots here because it's much more difficult for people to get measurements of damping, especially at those frequencies, those low frequencies. So just a few, but nevertheless, it gives a very nice characteristic, which gives you a correlation, which will then allow you to identify what the frequency is and what the damping is, and therefore what the expectation is for the way that a structure will behave. Remember, though, that you must exclude these nonlinearities of having left the linear elastic range or you've got too much soil structure interaction. And the risk ratio allows you to use that equation and then compare what you've got with what the code says you should have and express that as a risk of operation of the structure. If you put those all into one diagram, the value of one here, the risk ratio, says you just met code of practice requirements. Some are much better, but there's a worrying number that are much worse. And that goes back to what we found with looking at the bridge population in the United States. And the insurance industry is keen on fragility curves. Now, if you take these fragility curves and look at them in terms of what the risk ratio does, then we take a single wind speed and look at the difference that will occur in risk ratio 1.5, 1, and 0.5. We actually find that for this wind speed, we've actually got an 80% loss for weak buildings. So the damage level is high. We come down to a risk ratio of 1, just met code, and it'll be a 5% loss. And then for a very strong building, then we get almost nothing. Retrieval of data from a remote site. Well, we have a structural cardiogram and we can run off solar power, use satellite communications. All of these things are advancing enormously quickly. This is an accelerometer. We are currently producing a new type of accelerometer, which will be based on the MEMS characteristics, and that means that prices will come down even further. Number of people tend to say, "Oh, it's too expensive. We can't do that sort of thing." Well, when it's only $1,000 or $2,000 and the responsibility for a building collapsing is several $1 million, it really is a no-brainer. We do have to worry about capacity as well. We will see, this is stress strain or displacement per unit force. And what we have here is the linear elastic range. And then we, hold on. I had an unwanted pop-up occur there. Okay. So as we leave the linear elastic range, then we get ductility occurring, and we have to be careful with what happens here. But nevertheless, what does happen is that the linear elastic range characteristic will move, and it is possible to look for changes in that. It's possible to look for changes in the risk ratio. And I do like to tell people that this diagram here, produced by a colleague of mine at the Building Research Establishment, was produced a long time ago. It's 5,000 years of the Earth's history in 50-year bunches. A red dot is a once in 50-year event produced randomly. So in other words, in a 50-year period, there may be a red dot or there may be several red dots. The once in 50-year event does not happen on the button as 50 years passes. Sometimes you get 3 or 4 in a 50-year period. Sometimes you get 2, 1. Sometimes you get none at all. So imagine if you start your career when there's 150 years of no 50-year period, you will probably be tempted to say, oh, they never happen. I know better than that. Whereas in practice, that's not the case. The statistics are unchanged. Now, if the statistics are changing, if we do have more and more windstorms, then gradually you'll find this is populated by more and more red dots as time goes by. And the risk will change as a result. Okay, we're back again. Just a moment. Okay, so damping itself has a three-part characteristic, and that was produced by Tom Wyatt and people doing experiments on pedestrian bridges. And it actually says, yes, okay, we get damping at low amplitude, which has a low amplitude characteristic, and then it rises depending on the material that is used in the structure, and then a high amplitude plateau where there's nothing left to dissipate energy. So what we actually get is this rising characteristic, which is actually dependent on the material used in building the structure. So we also have databases now which include the 40 forced vibration tests, and predictors for damping are based on this now quite large database. What's damping? Well, if you actually excite a structure and allow it just to decay in oscillation, it will continue to vibrate, but there will be an envelope to the vibration. And that actually says what the decay is. The curve there, the envelope curve, is e to the minus zeta omega nt. So if you know omega, the natural frequency, circular natural frequency, then you can calculate from the rate of decay of this curve what the damping is in the structure. Now, on top of that, we've actually got something which says, okay, we've got this three-part curve. If we have damage, what happens? Well, at low amplitude, the plateau rises. If you've actually destroyed something inside the structure, if you've got damage, then what you get is a rotation of this characteristic. And if you've used up a lot of the energy dissipation mechanism, the total characteristic will reduce. Now, if you actually look at this characteristic produced by Yuko Tamura in Japan, he said there is some information which suggests that damping may decrease at very large amplitudes. That would be horrible if it really is true, but there is. And in fact, um, measurements made at very large amplitude suggest that that might be the case. So, can we do that for all types of bridges? Yeah. Stone arch structures? Yes, they're precise. Cable stayed structures? Yes. Although they actually have higher values of damping than experience with other structures would suggest. would suggest. Cable hangers can introduce the energy loss by themselves. It's predictable for viaducts as well. The European Commission has actually said there are three types of damping, basically material damping, structural damping, and interaction damping. And you need to take into account all three of them. Now, this is the Iron Bridge in the UK. It was built in 1781, and in fact, Thomas Paine built a model of the Iron Bridge in Paddington in 1786. The name Thomas Paine may be familiar to you. He's one of the founding fathers of the United States. So what we actually have here is energy dissipation. Where do we get it? Well, we have energy inside the material of construction. We have energy dissipation at the joints. Differential movement at the joints causes that. We have energy dissipation into the foundations. We have energy dissipation by interaction with the air. That can be a problem sometimes, but at low amplitude it tends not to be. And then we have friction interaction with adjacent structures. So indications of damage, changes to the dynamic parameters in any mode of vibration, and that is frequency, damping, and mode shape. So the dynamic signature memorializes the condition of a structure. It includes hardware, software, algorithms to capture the dynamic response to the structure. We need to measure frequencies, mode shapes, damping, and displacement. And it'll take 1 to 3 hours of continuous monitoring. That's all. Then how do you extend the life of a bridge? SHRP2, produced in 2013, was the second strategic highway research program, and it assessed service limit states more accurately, provided actual service performance data of real structures. It was component-based distress models, and It gave specific guidance about elements of a bridge. It was reduced by the Federal Highway Administration, the ASHTO, and by the Transportation Research Board. How can we measure? How can we extend the life? Measure the performance, measure the holistic behavior, calibrate existing models like finite element models, and learn. Just by the way, most bridges are given a test in a wind tunnel before they're built. You can identify a number of things that are useful for that model. What you can't do is identify exactly how much damping there is in the structure itself. So measurement of dynamic behavior actually identifies all of the problems identified in SHRP2. This is notional, but nevertheless, if you have one bridge and you decide to do a lot of maintenance on it, then the build costs a little bit more originally, but as we get up to say a 40-year period, then suddenly you've got a big renovation as necessary for a bridge which you pay a reasonable amount for maintenance year by year. You'll find that you avoid that big problem, and over perhaps a 50-year period, then you find that you've actually got a big saving in money. Now, I'd like to give you some examples of real life response to bridges. First one is the RFK complex, and then I'll lead you through some others, which I think you may well find interesting. This is the RFK complex, which is previously known as the Triborough Bridge in New York City. It consists of three parts: a suspension bridge, a lift bridge, and a truss span. We measured all of them. And we measured that by putting these triaxial accelerometers attached to a part of the structure itself. As I said, you don't need to make a lot of measurements. All you need to do is make sure that you've got the holistic behavior. And what we found was this. On that suspension bridge, first mode, the one that you would normally assume was the only one needed for design, 0.195 hertz, one cycle every 5 and a bit seconds. So that was the first order vertical bending mode. And then we had 0.22 hertz, a transverse motion, upstream, downstream, first transverse bending moment, and then 0.244 hertz, vertical mode, second order east and west side in phase. So what we've got here is in a realm of 0.05 hertz, we have three modes of vibration, and these can all transfer energy from one to another. So we measured a number of others as well. I'd like to just show you 0.195 hertz was this, and you'll see east and west side of the bridge, which was what we measured, we found very slight differences in some places. This is the amplitude of the response. So what we're saying here is that there is less stiffness in a certain place. What we'd done here was to take an accelerometer and move it, make measurements at a single place. We don't have to put all of these accelerometers in position and measure them continuously. A traveler will do, and the amount of time that you need to spend there is much less. So then 0.22 hertz, we've got east and west side. Again, we've got a stiffness anomaly in a certain place, and the east and west sides are moving independently. Then we've got an anti-symmetric mode at 0.244 hertz. And then we've got and this is the two sides of the bridge are operating in anti-phase. So when one goes up, the other goes down. Higher frequencies. This is 0.6 hertz, and we find another stiffness anomaly on the west side, picked out by this higher frequency, this mode 8 frequency. In fact, there's still remnants of that stiffness anomaly in the same place in this mode as well. And that's the bridge that this identification of vortex shedding actually occurred. And we could measure the response of the main cables of the bridge, again, simply by attaching an accelerometer to the cable, making sure that our own signal cables were not flapping about, because if they do, they might give a signal to the accelerometer themselves. And you'll notice we did not need to close the bridge to be able to do these measurements. So that's the main span. And we looked at the approaches to the bridge as well. So this is the main span over here and the approach over there. And we found that there was an interaction between the side span and the main bridge as well. This is a mode 2.391 hertz of the side span. And then the lift bridge. Here's something interesting as well. The first mode was the entire thing moving horizontally, left and right. The thing was that just before this was a toll bay. And if you imagine you pull up a toll bay, and what do? You accelerate away. Even if it's gentle acceleration, you are creating a force. So this type of mode was actually excited by people coming away from a toll booth. And again, we have modes of vibration which are similar to the ones that occur in the main span, because they're the sort of thing that's expected of a bridge deck. But in this particular case, we had something in the middle, which was a stiffness anomaly. The lift bridge, well, we had damping, which was quite large in various, well, by comparison, it was quite large, 2.5%, whereas it's only 1.5% as the amplitude increases. And those are the frequencies with damping rather larger than those for the main span. We were also able to measure the vertical response of the towers, and we can do that by using an accelerometer again and seeing what the structure and the ground forming a continuous situation, the system actually do. And then the Bronx Kill Bridge, and we were able to look at what the response of that was. This is the Manhattan Bridge, again in New York City. And in this case, you'll see there's not only road traffic, but there's rail traffic as well. Now, in this case, we did close one lane. And the reason is that we were looking at the response of the hangars. It was found that some of them were flapping about. They were not well tied in. So what we did was to measure. Additionally, we found this is Manhattan Bridge, and we looked at some cracks which had occurred over a long time and identified what those were with strain gauges. And of course, the Manhattan Bridge, we were looking at hangars. We can do that by saying that the frequency is the torsion upon mass per unit length upon 2 times the length. So if we measure the frequency, we've got a direct measure of the torsion. So we were able to. We measured the frequency, and we found, knowing the length of each of the hangers, that we had this. Now you can see here we've got the main bridge frequency, and we've also got the hanger frequency as well. This is one of a different length, and this is one which is not fastened well. I think you can see quite well what the problem is there. That as as the amplitude changes in for this hanger, then you get a different frequency. Same way you do in earthquakes. So we identified exactly what's necessary, but it does say, okay, we get extra energy dissipation if we don't have the hangers at the right tension and correctly tensioned and well attached. And there we can also see some orthogonal activity because the hanger doesn't move in only the north-south, it moves east-west as well. Here we have rail truss bridge, and in this particular case, we were looking at the response to trains coming through, and we found modes of vibration antisymmetric here. Again, normal sort of response straight up and down, antisymmetric. And then what we found was individual elements of the structure not actually connected well to other parts. And in practice, this is because the steel elements had holes in the end through which they put bolts, assuming that if you strung 3 or 4 of these together, then you would actually get a compound type of behavior. Well, it's not true. Some of them were just rattling around. Then there is an ordinary concrete bridge. We looked at this one because of rusting occurring. And we're having a look to see if the performance was okay. Well, in practice, it gave us some very good information. We saw that it was. We found natural frequencies, and we used a finite element model, partial finite element model, to simulate what the characteristic was. And then we used a truck which was laden, and we measured what the response of the structure was. And in practice, what we found was that we got slight differences which occurred, and we were looking for this, and this is over a period of 1 hour. The truck on girder 1 to start with, and then on girder 2, girder 3, girder 4, and so on. So we could measure the change in stress as the truck went over. 4 passes provided repeatable. You can see truck on girder 2, and we've got effectively the same amount of transit of the stress characteristic. Now, if we look at what that means, what we actually have was the amount of strain in the structure and the frequency in the span. So as we look at this, the strain was higher, and here it's lower. The strain comes down, and the frequency comes down as well. This is for the a whole series of spans which were a similar length. So we got a good measure of what was actually going on the structure itself. In this particular case, we had the Saugus Bridge in Boston. We could use damping as a measure of energy dissipation, and we identified what the response of this bridge was. Why? Because they had a problem with it. And if I just move on to an assessment, the bridge was known to be failing underneath. Did that make a difference? Well, yes, it did. We were monitoring what was going on and were able to tell them very quickly that there was a trend in the characteristics. So we took out both times when a train was on the bridge and when it was not. And by taking that, then what we had was two different situations, and we're able to look at this. What we found was that acceleration in the vertical direction, you can see a westbound train going over there. The east side caused a problem. In the west side, it caused a problem as well. So we were able to identify it and to say, you have a problem. You need to do something about it. So they did close one side and commented, this is the first time that we've ever known exactly what is going on. So we calibrated our finite element model, and in practice, what we found here was first mode of vibration, 0.5 hertz by measurement, and the model said 0.48. That's pretty good. If you're looking for design, you would be very happy to have that sort of correlation. Well, it wasn't so good for the second and third mode. It wasn't any good as far as the others were concerned, because we measured a whole series of modes of vibration. Excuse me. And the finite element model didn't predict them at all. So we stuck with our first three and were able to work with that. This one, I'm going to just pass over that quickly because we're running short on time. However, this is a bridge which has pile driving close to it. And you can see that pile driving created a 33 hertz response from the front pile driving, but it also beat with 4.5 hertz, which was the resonance frequency of the bridge. And you do have to be careful of this sort of thing. Post-tension buildings, you can take local measurements, cable response. We can take measurements quickly, and we can take global measurements to get the structural response. So the question is, okay, you've been talking about long span bridges. What about short span bridges, small ones, multi-span, and they're built of masonry? So we looked at this bridge in Australia. And in practice, it was in a very poor condition. They assumed. So there had been stiffness elements added to it. And what we found was modes of vibration doing this sort of thing, incorporating motion in one span, two spans, three spans there. And we measured frequency and damping, which meant that we could identify our risk ratio. And we could then say, okay, we can calibrate our finite element model. We can look at the modes of vibration. And the big question for the owners of the bridge was, can we drive a train faster over the bridge? Now, they were very keen to be able to raise that speed restriction because this is an iconic train in Australia. The Indian Pacific travels from Sydney all the way across to Perth. Pretty much a similar journey as from New York to Los Angeles. And it does it every day and goes 4,000 miles there and back. So by identifying the modes of vibration, we calibrated the model, we put in the weight of the train and had a look at what the response was going to be and said, yes, the speed restriction is not a problem. You can raise it. And they like that. So general assessment of bridges. Firstly, wind tunnel tests are good, but incomplete because aerodynamic damping is addressed, but structural damping is not. The design requirement actually requires that damping be estimated. So you do all of these tests in a wind tunnel. You put on forces which are identified, that they reflect the Earth's boundary layer well, and you build your structure so the interacting elements are a good representation of the structure. You do all of this, and then you guess at damping. And it's complex because it's both structural and aerodynamic. So the measurement of whole body response allows the assessment of the actual complex response of the new structure. But of course, you can't do that when you have a wind tunnel before building of a bridge. But it's as well to check it after it is constructed. I'm going to move over that quickly. So yeah, we can do rapid assessment of structures these days. We can do it in just a few hours. We can calibrate models. We allow safe redevelopment as well, and it gives peace of mind as to what's going on. Now this is the Western Suburbs Bridge in Seattle, and they had to close this bridge because of problems which they found by looking for cracks in the structure. Closed for a long time, which just divided the city in two parts. If they looked at the holistic behavior of the entire structure, who knows what they might have found. But anyway, they went on their way and closed for several years. So, ladies and gentlemen, thank you very much indeed for your attention. Please, I hope you've enjoyed this, but be prepared for potential surprises that occur in the natural world because we are in a changing environment and we must be ready for it. Thank you. So I'll be happy to answer questions if there are some. So I have a question from James Mackay. Why aren't the new Tacoma Narrows bridges classified as suspension, not cable stayed? Yes, they should be really. Mm. James, you're absolutely right. They could be. The problem that occurs is that most bridges these days, as you saw in the Florida International Bridge, uh, um, then they're a mixture of different types. So when we have that occurring, it's difficult to define them exactly, but yeah, they're mainly suspension in that particular case. Okay, any other questions? Okay, well, thank you very much, and I hope that you'll be able to answer all the quiz questions, and get your PDH awards for 2 hours. Ladies and gentlemen, thank you very much indeed.
Hi. Yes, that's me.
Okay, have they got it all okay?